Trajectory prediction is a cornerstone of autonomous driving, essential not just for understanding what's happening on the road, but for building accurate world models that can anticipate future motion. Modern systems rely heavily on large-scale, data-driven predictors trained on massive datasets like nuScenes, Waymo, and Lyft. These models achieve impressive accuracy and controlled, in distribution settings. But here's the problem. Real-world driving environments are unpredictable. Road layouts change, traffic behaviors vary, and driving styles differ across regions. When a model trained on one dataset is deployed in a new environment, say, from nuScenes to Lyft, it often suffers from severe performance degradation. This is due to distribution shifts, the mismatch between training and test data. Traditional approaches assume the model is fixed after training. But what if we could adapt it on the fly, during real-time operation? That's where test-time training comes in. Test-time training allows a model to learn from new data as it arrives, using the very same observations that serve as input to make predictions to generate labels for previous predictions. It's a form of auto-labeling, making it uniquely suited to trajectory prediction. The idea is simple. Update the model online using the latest data to better fit the current environment. But here's where things break down. Existing test-time training methods fall into two major traps. First, they rely on an offline pre-training stage that optimizes for static, in-distribution performance. But that's not what matters at test time. The model needs to be ready to adapt, not just accurate. This creates an offline-online misalignment. The model is trained to perform well on data it will never see again, while the real challenge is how fast and effectively it can learn from new, unknown data. Second, most methods use fixed learning rates and rigid update rules, predefined, one-size-fits-all strategies that ignore the actual characteristics of the incoming test data. A sudden shift in traffic density or a complex intersection might demand a different learning rate, a different update frequency, or even a focus on specific challenging samples. But current methods don't adapt, they just keep going. To solve this, we introduce MetaDAT, Meta Pre-Training and Data Adaptive Test Time Updating, a new framework that rethinks both the pre-training and the online adaptation phases. Let's break it down. Part 1, Meta Pre-Training, training the model to learn how to adapt. Instead of training a model to be accurate on a static dataset, we train it to be adaptable. We use meta-learning, learning how to learn, to simulate test-time training tasks during pre-training. Here's how. We treat individual driving scenes as distinct subdomains. Each scene has its own unique road layout, traffic patterns, and agent behaviors. We split the source dataset into these scenes and simulate online test-time training on each one. In a bi-level optimization process, the model undergoes multiple simulated adaptation steps, each time updating its parameters using gradient descent on past predictions. Then, we evaluate how well it adapts after those steps, and use that performance as a meta-objective to update the initial model parameters. This means the model learns not just what to predict, but how to adjust quickly and effectively when faced with new data. The result? A flexible starting point, optimized not for static accuracy, but for rapid, robust adaptation. This solves the offline-online misalignment. The pre-training stage now directly prepares the model for the realities of test-time learning. Part 2, Data Adaptive Test Time Updating, learning on the fly intelligently. Now at test time, we don't rely on fixed rules. Instead, we introduce two key innovations. First, Dynamic Learning Rate Optimization, DLO. We monitor the online partial derivatives of the loss with respect to the learning rate. Using a first-order approximation, we estimate how the loss would change if we adjusted the learning rate. Then, we optimize the learning rate itself in real time, using the gradient of the loss with respect to the learning rate. In practice, we average gradients over a window to stabilize training, and we apply different learning rates to different layers, because deeper layers may need different adaptation speeds. This ensures the model adapts at the right pace, based on the current data, without manual tuning. Second, hard sample-driven updates, HSD. Autonomous driving data is long-tailed. Most scenes are routine, going straight, turning at a simple intersection. But a small fraction, like complex merging, high-speed interactions, or map-dependent maneuvers, are critical and highly sensitive to distribution shifts. We identify these hard samples by comparing prediction errors to a running mean and standard deviation. If the error exceeds the mean plus 3 standard deviations, we flag it as a hard sample. Then we perform additional updates on these samples, focusing computational effort where it matters most. Meanwhile, we skip learning rate updates on these samples to avoid destabilizing the model. This is a massive efficiency win. We don't waste time updating on easy, uninformative data. We concentrate on the most challenging, informative cases, making adaptation faster, smarter, and more effective. Results: superior accuracy, robustness, and efficiency. We tested MetaDAT across multiple cross-dataset shifts. nuScenes to Lyft, Lyft to Waymo, Waymo to nuScenes. Under both short-term 1's watch, 3's prediction, and long-term 2's watch, 6's prediction settings. On the standard best of 6 metrics, mADE₆ and mFDE₆, MetaDAT consistently outperforms all baselines. It beats the previous state-of-the-art T4P by 12.7% on mADE₆ and 12.5% on mFDE₆ in short-term prediction. Even more impressively, it outperforms AML, a meta-learning-based method, by a wide margin, showing that our full model pre-training and adaptation pipeline is far more effective than just adapting a single layer. And it's not just about accuracy. We tested robustness to bad initial learning rates, where T4P's performance collapses under suboptimal settings. MetaDAT, thanks to DLO, adapts gracefully. Even with a poor initial learning rate, it recovers and performs strongly. We also evaluated real-time efficiency. On a single NVIDIA L4 GPU, MetaDAT maintains high frame rates, improving prediction accuracy without adding significant latency, thanks to hard sample-driven updates that reduce unnecessary computation. In few-shot scenarios, just 2,000 test samples, MetaDAT still dominates, showing strong few-shot adaptation capability. Qualitative results confirm this. In complex scenes, like merging at intersections or navigating dense urban areas, MetaDAT produces more accurate, diverse, and plausible trajectories than joint training, no adaptation, or T4P. Why this matters? This isn't just a technical improvement. It's a shift in philosophy. Instead of treating models as static artifacts, we're building systems that learn continuously, adapting to new environments, new behaviors, new roads. That's essential for real-world deployment. And MetaDAT does it all with minimal assumptions. No need to know the target domain in advance. No need to hand-tune hyperparameters. The model learns how to adapt on its own. Final thoughts. In a world where autonomous systems must operate in unpredictable environments, adaptability isn't a luxury, it's a necessity. MetaDAT bridges the gap between pre-training and real-time learning, combining meta-learning for powerful initialization with data-driven, intelligent updating. It's faster, more accurate, more robust, and more efficient than existing methods. And it sets a new benchmark for test-time training in trajectory prediction. This is the future of autonomous driving, not just predicting the future, but learning it as it unfolds.